and so on. And so it can find places where you're using memory that's uninitialized, reading or writing memory after it's been freed, or off the end of malloc blocks, memory that's returned from malloc. It can find memory leaks, and it does impose a significant overhead in terms of runtime that can be as much as 20 or more. We've used Valgrind in the past here as a software development organization, and we think it's very good. And it's open source, so you can go and play with it right now. Probably the most common static analysis tool that people have heard of is lint, and I highlight here on this slide SPLint, which is an open source version of lint that you can go and download now. Just to give you a little bit of background on lint, lint has been around forever, and in fact was invented by a gentleman named Stephen Johnson back in 1977. And I want to read to you a quote that he gave in implementing lint and kind of his manifesto on lint. And it goes like this. It says, "Lint tries to give information with a high degree of relevance. Messages of the form XXX might be a bug are easy to generate, but are acceptable only in proportion to the fraction of real bugs they uncover. If this fraction of real bugs is too small, the messages lose their credibility and serve merely to clutter up the output, obscuring the more important messages." So he had that observation, almost 30 years ago, about the real need for high-fidelity results out of a static analysis tool. And whether or not lint got there, well, given the fact that we don't see lint everywhere in every development organization using it, my guess is it didn't quite get to that, because a lot of people do look at what lint produces and says, "Oh, it's a lot of fluff. It's, not helping me with the runtime issues in my code." But lint has been out there for a long time. And it suffers from a couple of the cons that I mentioned before about really not understanding how the whole system is built, because it is a source file by source file type of analysis. But if you want to give that one a try, you can certainly go to splint.org, and it's been extended in these efforts to dig out security vulnerabilities on top of the typical lint warnings that you would see. And then, of course, from a commercial standpoint on the dynamic side of things, there's Purify, and that's probably the one that people have heard of the most. Back in 1991, a gentleman named Reed Hastings wrote the first version of Purify, and it is a memory debugger that is similar to Valgrind, instruments the code. It doesn't do the translation, but it does instrument the calls to malloc and free and other interfaces for memory manipulation, so that it can keep an eye on those things. It was commercialized back in 1991 through Pure Software, which then was later merged with Atria, of course, the provider of ClearCase, and then acquired by Rational, which then became IBM, which is now part of the Rational piece of IBM. And over the last 16 or so years has gained a tremendous amount of deployments across the board. Another nice side note about Reed Hastings, he took the success that he had with Pure Software, and he is actually also the founder of Netflix. So for those of you who know about Netflix or use Netflix, the same guy who did Purify did Netflix as well. And so it's probably one of the most widespread dynamic tools out there. And then finally, on the commercial side for static tools, well, I'll start plugging Coverity a little bit. We've been providing static analysis solutions for the last 4+ years, and our technology is actually based out of research that I did with a number of my colleagues at Stanford University. And we have spent the last, almost decade now trying to figure out the problem of how do you take static analysis and solve a lot of those cons. How do you understand the build system behind how you put the software together so that, the pieces all are in place for the analysis engine, and it has the right representation of the code from the compiler and from the build system, so it can analyze something that's as close to your executable as possible to give you the highest fidelity results. And we've had a lot of success doing that over the last number of years, and we've got a couple of hundred customers who are using it every day in their development process. And so we'd be happy to come out and show you how we can improve your software quality with our particular static tool. So before I take a few questions, I just want to wrap up and say, revisit the original question of the webinar: what bug spray should I use? And the real lesson here is that these are fundamentally complementary technologies. You should really use both. And, because the duality between what you can find at compile time using the static techniques and what you can find at runtime using the advantage of actually instrumenting the code and watching what's happened on a particular execution path, they're going to find different things. And they're going to be used to find different kinds of bugs that are causing different kinds of pains. And, the recommendation is to, of course, set your expectations correctly for what each tool should be used to find. Like I said at the beginning, I still see a lot of confusion out there, and people ask, well, how does, Coverity compare to Purify? And the answer is, well, it doesn't really compare that way, because they're used for different things to find different kinds of problems that manifest themselves in different ways. And in fact, I was actually speaking with one of our customers just this morning who was telling me about how they use both Purify and Coverity in their development process. And they run Coverity very regularly, almost daily, and they run Purify every week on the test cases that they have to make sure that there aren't any memory problems that have seeped in, because they understand that they are complementary, they should be used in concert, and that's how you really benefit from the strengths of both, and you should leverage the strengths of both. So it's not really an either-or, and they're both dynamic and static tools are going to help you write better code. So with that, I'll take a few questions. So let me look through here. If you'll just give me a few seconds to read through some of the questions and pick out a few before we end. The first one is, how does Coverity enhance the security posture of the application? So just to kind of keep it on topic, the notion of security vulnerabilities are something that static tools can do that dynamic tools can't do really as well, in the sense of watching what's happening at the particular runtime through instrumentation of the code. This is partially because you need to know how data gets in. And the static tool, what our static tool is able to do in that regard, is it's able to identify the tainted data as it's coming, into the system. You can specify to the analysis, here is exactly where the tainted data is, and it can use those to watch the flow of that data throughout the system. On the dynamic side, of course, if you were to take a similar methodology, you would only identify a problem if that particular execution had a security vulnerable, or had a security exploit in it, if that tainted data was getting to a place it shouldn't have gotten to. So in some sense, this is an advantage for the static tools, and one of the reasons I mentioned that the scope of defects that dynamic tools look for is a little different. Here's a good question. After using static tools, what kinds of bugs do you expect the dynamic tools to catch? And the reason that's a good question is because it really gets into where the limitations of the static tools are. And again, it very much depends on the static tool, but I would say in general, a static tool, there are plenty of constructs that can cause a static tool to lose information about the system. We can't solve the halting problem. And what that means is, at runtime you can't, or at compile time, you cannot figure out everything that's going to happen in the code. So the runtime tools are going to pick up the defects in the categories that overlap, resource leaks and null pointer problems and those types of things. They're going to pick up the defects that the static tool had to throw out and not report because it didn't have enough information about the code to make a determination that it really was a defect. This could be for a number of reasons, again, depending on the static analysis tool. It could be because there was complicated data flow, and the pointers actually got to the point where the level of pointers throughout the data flow went beyond what the analysis was keeping track of, and as such, it could not determine whether or not memory was freed or which memory was allocated, or if the alias analysis was there that didn't quite understand how the pointers were pointing to the same thing. Those are the places where it could get tripped up. So the dynamic tools pick up those things. Okay. Are there any static and dynamic tools